Welcome to Codeup's Data Scientist Day. My name is Jason Strad. I'm the co-founder and CEO of Codeup. To kick off this Data Scientist Day, I would like to give you a formal introduction to Codeup. Thank you.
Thanks, Jason. Hi, I'm Stephen Salas, Director of Business Development. Codeup is a 22-week career accelerator that trains data scientists across the entire data science pipeline and then places them at companies like HEB, EY, USAA, and Booz Allen Hamilton. In the Capstone projects you're about to see, they worked in teams as full-time data scientists to deliver actionable insights. And to kick off our presentations, here's Project Danger Zone.
San Antonio is the 7th largest city in the country, and as it becomes more populated, the number of drivers increases. Unfortunately, every year, there are about 50,000 motor vehicle accidents in Bexar County, and nearly 17,000 people get injured. Here is a brief overview of our presentation today. I will be one of the presenters. My name is Anna Vu, and my team welcomes you all to Project Danger Zone, an analysis of 2021 San Antonio accidents. It is my honor to introduce our team of data scientists. From left to right, we have Xavier Carter, Robert Murphy, myself, and Ray Zapata. We form Project Danger Zone to let data-driven insights take the wheel.
So my task with the pipeline focused heavily on the acquisition of data. Usually the data that we work with in the scope of the curriculum has been focused either on primarily CSVs or utilizing SQL. But I wanted to take a different approach and use Selenium, a Python library for web scraping JavaScript rendered websites. Using myaccident.org, after setting parameters between February 14th and August 8th, I was able to acquire the links for about 40,000 unique accidents in the San Antonio area. I then created another program utilizing Selenium that would parse through each link and extract all the valuable information off of them in order to tackle the question at hand. Utilizing the Google map provided by the website, I was able to extract the latitude and longitude from the picture. Other variables that were extracted were the location, date and time, the weather, the speed limit, number of vehicles, number of injuries, number of occupants, accident factors, as well as road conditions. I was able to grab driver-specific information as well, such as the age, gender, driver's license status, as well as where the damage occurred on the vehicle. Car-specific information was limited, as it only provided the make, year, and color of the car, as well as a redacted VIN number. So we utilized an API by the National Highway Traffic and Safety Administration to use that redacted VIN number to acquire the specific vehicle type for each vehicle. Stepping into preparation, standard cleaning strategies were utilized, such as fixing data types, handling missing values, encoding variables, as well as some feature engineering. We also touched on some natural language processing techniques and to get the key contributing factors from the accident narrative. After all this, acquisition and preparation was complete, and with a tidy data set, we could now begin to start exploring our target variable.
Upon initial exploration, we noticed that none of the features had a strong correlation with injury status. In fact, most had almost no correlation at all. We also noticed that our data is imbalanced, as seen with the target distribution on the right side. We had to find ways to combat the imbalanced dataset for model use and try some clustering to see if combining features can help predict injury better. The best performing clusters uses a combination of these 4 features: where the vehicle was hit, the vehicle type, speed limit, and airbag deployment. Clusters created with these variables were evaluated using a chi-square test with respect to injury status. They all had p-values of nearly 0, meaning we can move forward knowing these clusters and our target variable are not independent. Every dot in this visual represents a San Antonio accident since February of 2021, plotted according to their longitude and latitude. We had hypothesized that injury rates were different depending on part of town, so we decided to split the accidents into 5 separate location clusters. So are there areas in San Antonio that have a higher injury rate? Well, statistically, no. Using ANOVA testing, there's not enough evidence to suggest that any of these clusters' injury rates are different from each other. So just be careful no matter where you are, because location does not exempt you from the danger zone.
Our initial hypotheses included that day, time, and date would play a role in injury rate. Exploring that, we analyzed the mean injury rate for each of the 168 hours in a week. Utilizing statistical tests between categorical hours and injury class, evidence was found to suggest a relationship between the two. We found that certain hours in the week had a substantially increased injury rate over the average 16%, the top 3 shown here circled. In those hours, The largest factor of cause was related to maneuvers, such as lane changes and merging. It was also found that average injury rate for the morning hours was virtually identical to hours afternoon. It was expected that certain events would play a role in increased injuries as well, such as the 4th of July weekend. Comparing with other Friday through Monday periods, while fewer vehicles were involved in accidents, the rate of injury was just over 2 percentage points higher during the US holiday. Statistical testing corroborated evidence of a relationship with injury. Additionally, over 11% of injuries during the holiday involved intoxication, more than twice the 5% mean for other similar time periods. Most people from San Antonio, whether fans or not, are aware of the Spurs basketball team's local importance, so it was a given to investigate game day impact on injuries. Using the 2021 schedule, we looked at days when a home game was played and compared them to all other days in the data. Due to varying start times, hours between noon and midnight were used to assess for significance. However, injuries were found to be independent of game days, even with consideration of distance from the venue. Though overall injury rates were similar, injuries related to speeding had an increased rate by almost 7 points. Lastly, in our exploration of time's relation to our target, is the period during San Antonio Fiesta. In 2021, this annual event ran from Thursday, June 17th through Sunday, June 27th. Injury rate during Fiesta was found to rise 3 points above the mean of all other 11-day periods that began on a Thursday. Statistical testing again showed evidence of a relationship between injuries and the Fiesta window. Unlike with other events we've discussed, no evidence of dependence was found with Fiesta injuries and any fault factors. Taking our insights and findings to the next phase, we'll discuss our use of machine learning models in an attempt to find the strongest drivers of injury.
So here we see the main features utilized within our model to predict injury. Features are broken down into categories to reflect whether it's an attribute of the driver, vehicle, or other. Other being crash location, the hour of day, the number of involved vehicles, and speed limit. So in order to find which features were the most relevant to predicting injury, feature selection needed to be implemented. In our case, we utilized RFE, recursive feature elimination. And essentially, RFE utilizes feature importance, and if a feature is essentially interpreted as weak, it's excluded from the model. So in summary, after implementing RFE, we ended up utilizing 16 features within our model. So in order to gauge the model, we need to have a metric to measure against, and this is where the baseline value comes in. The baseline is a metric to measure model performance to discern the validity of a model. And the baseline is predicting the most common observation, which as previously shown was non-injury. And since we're utilizing a binary classification, the imbalanced dataset has resulted in a baseline accuracy of 84% and a recall of 0%. So in the case of our model, we don't want to focus on accuracy. So that begs the question, what do we want to focus on? So in order to gauge our model, we will need to reevaluate on a different metric, and recall is the most viable. We have defined positive cases as predicting injury and negative as non-injury. So the worst case scenario for our model would be predicting non-injury when injury has actually occurred. So the best metric to use in our case is recall, which focuses on the positive cases. We ended up utilizing 4 models: k-nearest neighbors, random forest, logistic regression, and gradient booster classifier, or GBC. The GBC model performed the best on the undersampled trained dataset with a recall value of 90%. So feeling confident in our model, we decided to evaluate the test dataset on GBC. This resulted in a recall score of 62%. So the model didn't perform better than the baseline in terms of accuracy, but the model is able to predict 62% of the time whether an injury does occur.
In conclusion, we were able to create a model that does what the baseline could not. Distinguish between when injury and non-injury occurs within an accident. Not only that, since our model tends to over-predict for injuries while optimizing for recall, this gives us more confidence when non-injury is actually predicted. Auto insurance companies could use something like this to detect potential discrepancies in injury claims. Knowing that insurance companies fork the bill for almost all aspects of an accident, including any bills related to injury claims, when a potential claim comes back that the person should have a low probability of injury, it allows this company to have more insight on specific possible claims that may need further investigation. Another great use for this model would be crash detection services and their collaboration with first responders when automating triage. When tough decisions need to be made and EMTs are short-staffed, this could be a great way for those respective parties to make more data-driven decisions on exactly where they should prioritize their efforts, saving not only tax dollars, but lives as well. Although our model would be able to tackle these given scenarios fairly well, there's definitely still room for improvement. So in the meantime, we leave you with these recommendations that can be utilized at this very moment. Those include safety awareness campaigns during holidays and large events, as well as increased law enforcement presence during high times of injury rates. For other iterations of this project and with more time, we would like to look into how the data was acquired to make sure the data was being collected in the best way possible. We utilize vehicle class with the damage zone, understanding what type of car caused the impact for each vehicle. We continue more exploration of variables and locate those causes for injuries. We'll look into acquiring the data in a different way, looking at each individual as opposed to each car during the accident. This may give us more insight as to what each individual was doing during the process of the accident, such as if they were wearing their seatbelt and their orientation in the car. We can also look at individual street analysis and looking at key roads in order to make sure we can improve infrastructure.
This may be the end of the road for us today, but we strive to continue finding what makes a danger zone in San Antonio as more data becomes available to collect daily. We hope to deliver actual insight to entities like TxDOT, Texas DMV, Barrett County Public Works, emergency dispatchers, insurance companies, and of course, the general public. Drive with us in the meantime. Always stay aware and focused of your surroundings. Protect yourself, family, friends, and others by commuting with care, and don't drink and drive. That concludes our presentation. On behalf of the Project Danger Zone team, we thank you for your time. If you are interested in taking the figurative highway to the danger zone by checking out our project in detail and to see future updates, please visit our organization's GitHub page by following the link here. Right into the danger zone. Until next time.
As you just saw, the Capstones are an end-to-end data science project. The teams start by identifying a problem and data set, forming a hypothesis, and determining stakeholders. Then, they wrangle real messy data to analyze, model, and visualize in order to form more actionable insights. Finally, they deliver their key takeaways and recommendations via these presentations. They worked on this entirely remotely as full-time data scientists, utilizing Zoom for daily Scrum meetings and virtual Kanban boards. With our next Capstone presentation, here's Team Houston, We Have a Pay Gap.
Hello, and welcome to Houston, We Have a Pay Gap, predicting current Texas public employees' salaries. More and more these days, companies and organizations emphasize values like diversity, equity, and inclusion, also known as DEI. Our team set out to tackle this topic from a data perspective, looking at a critical data point, salary figures. Using data acquired from the Texas Tribune, we created a model that predicts a government employee's annual salary based on demographic information, tenure, and job description. Before diving in, I'd like to introduce you to our team and agenda. My name is Christopher Mayorga, and after I share the highlights and overview, Forrest McCroskey will take us through acquiring and preparing the data. Next, Desiree McElroy will answer some key questions uncovered in our exploration. Finally, Mariam Naqui will go over our predictive model and conclusions. To start, we define the scope of our project. We ask questions like, are there inequities in annual salary based on race or gender? And is there parity along race and gender among elected officials and directors? We found some serious inequities. For example, women working for the Texas state government make 88% of what men make. Among directors of state agencies, white employees outnumber Black, Indigenous, and people of color by a ratio of 2-to-1, compared to 1-to-1 within the Texas general population. Finally, we offer recommendations to the Texas state government, like standardizing director salaries to eliminate arbitrary biases and implementing a strategic DEI plan across all state agencies. To start, let's take a closer look at the use cases for this project. Aside from offering specific recommendations to the Texas government, we also aim to provide a methodology for companies and organizations who seek to analyze their own demographic and salary data. For example, the chart you are seeing now breaks down racial demographics by agency. It's clear that white employees outnumber other racial groups in some key departments, such as government admin and representatives, especially when compared to the overall Texas population. With access to the right data, this chart could be replicated at your own workplace. What might those results show? Next, we zoom into average salaries by race and gender, where we can already start to see some disparities. Looking at this visual, we can see that, with the exception of Asians, Black, Indigenous, and people of color make less than the statewide average salary. With the right leadership and data reporting, companies can improve employee satisfaction and reduce turnover, all while sticking true to their values. Now, Forrest will walk you through our tools and data pre-processing.
Thank you, Chris. Below are the main tools we use to execute the data science pipeline for our dataset. For project planning, we use Trello board to maintain an agile workflow, as well as Google Drive for efficient team editing on all documents. The primary platform for our project is a Python notebook in Jupyter Lab, where we use pandas and NumPy to prepare the data. For data exploration, we use Matplotlib and Seaborn to visualize variable relationships, then utilize the scikit-learn library to build our regression models. Last but not least, for the final phases, we use Canva to design our slides before importing them into Tableau to provide interactive visuals. Now let's talk about the initial phases, acquiring and preparing our data. First, we acquired data from the Texas Tribune's Government Salaries Explorer as a CSV and converted it to a Pandas data frame. After viewing the data types and observations, we did not have any null values and only ended up dropping 4 duplicate rows. In order to make an easier workflow, many columns were renamed for a more human-readable format, and columns with string values had leading and trailing whitespace removed. And finally, each observation contained a hire date for their position, and this was converted to a datetime object for feature engineering purposes. And now we have my personal favorite, feature engineering. In order to answer our key questions and explore different inequities in annual salaries, categorical columns were created for each race and gender included in the dataset. We also categorized further and formed columns for employees with director positions and elected official status. Then finally, with domain knowledge from our data source, we were able to create tenure columns in both months and years for each employee by subtracting the hire date of each employee from the time of the last source update, which was July 1st, 2021. These features all provided multiple insights while exploring for inequities in annual salaries. Now Desiree will walk you through how we use them to answer our key questions and what we found.
Thank you, Forrest. Like mentioned earlier, we were able to generate new features, which in turn posed new questions. First, are there inequities in annual salary based on race? Let's start by looking at our donut chart with demographic percentages. Notice how the count for white employees makes up just below half of the overall count of employees. Below, we can see a stacked frequency chart of annual salary with race as a filter. As you look at the lower ranges on the x-axis, salaries are fairly evenly distributed across the races. However, as we transition to the upper ranges of annual salary, the amount of white employees increases, leaving the other demographics falling behind. Based on this, we can conclude, yes, there are inequities in salary based on race. This leads us to our next question. Are there inequities in annual salary based on gender? In our donut chart, you can see that female employees account for over half of the total. Below, we can see a stacked frequency chart of annual salary with gender as a filter. As you look at the lower ranges on the x-axis, we can see that the majority of these positions are held by women. As we approach the upper ranges of annual salary, men far outnumber women in higher paying positions. Again, this leads us to conclude, yes, there are inequities in annual salary based on gender. What about leadership positions? Is there parity along race and gender among elected officials and directors? Recalling the donut chart from our initial key question, white employees make up 45% of total employees. However, if we filter for directors, that percentage jumps to 70. Furthermore, when we filter for elected officials, the percentage for white employees jumps to 67. In both cases, filtering for these features the percentage of white employees jumps to well over half. We can see this in the bar chart below, which represents the raw number of employees for each demographic. You'll notice that the amount of white directors greatly exceeds any other demographic. It is obvious minorities are severely underrepresented in these leadership positions. What about gender parity in leadership positions? Female employees account for over half of the overall total, but for director positions, the count lowers to less than half. Even more so for elected officials, the count of women plummets to only 33%. That's only a third of the original count. This data gives us an eye-opening view on correlations to annual salary. Next, Miriam will explain our modeling portion of the presentation.
Thank you, Desiree. We're predicting annual salary, which is a continuous variable, so we will use regression algorithms to build models. We use gender, some race variables, tenure, and if an employee works part-time or in a classified role to predict annual salary. All our models will be fitted on the trained dataset to maintain data integrity and prevent data leakage. After the models are trained, we will evaluate model performance on out-of-sample data using the validate split. Only the best performing model will be evaluated on the test dataset, which will give us an indication of our model's performance in the wild. For our model evaluation metrics, we use the root mean squared error, or RMSE, and R squared. RMSE is used because it has the same units as our target variable. R squared is the explained variance you see on the right, which means the variance in the data that is explained by our model. The best model will have the highest R squared and the lowest RMSE. We created 4 different regression models, which you can see on the left. Our best performing model is the second-degree polynomial regression model. This RMSE on the right shows that our model's salary predictions are off by $21,000, and the explained variance score, or R squared, shows that 31% of the variance in annual salary is explained by our model. And now, the moment you've all been waiting for. Houston, we have a pay gap. We use average annual salary proportions of each subgroup to find the cents per dollar difference. We found that for every dollar a male employee makes, females make 88 cents. For every dollar a non-Hispanic employee makes, Hispanic employees make 90 cents. And for every dollar a non-black employee makes, black employees make only 82 cents. We will go one step further and control for all external factors. Some people might suggest that women take lower paying jobs and that's why they have lower salaries. So we will compare employees of the same race and job title, and we found that women make 93 cents for every dollar a man makes. For Black and Hispanic employees, the pay gap actually increases by about 10 cents when controlling for external factors. To conclude, we found inequities in pay based on race and gender, and an overrepresentation of white men among elected officials and directors. Our best model does not perform as well when predicting salaries in the upper and lower ends. Ideally, there should be no connection between an employee's salary and their race or gender. However, the fact that our model can predict salaries based on race and gender indicates there is a problem. So again, our recommendation to the Texas state government is to standardize salaries for all employees so these factors do not come into play, and implement DEI initiatives across all state agencies. We would also like to look at historical salary data to predict compensation trends. And now, on behalf of the data science team, I thank you for your time and attention. Please do not hesitate to contact us with any questions.
From working in teams to presenting complicated data, communication skills are critical. Understanding data is only half the story. Telling the story that the data represents requires an additional skill set: storytelling. Data scientists need to effectively relay their recommendations to stakeholders. This was one of the top desired skill sets we heard from our interviews with employers, and also one of the hardest to find. Our next team is excited to share the story of their data with you. Here's Team Tech Blues, Mental Health in Tech.
Hello everyone, we are Tech Blues, and today we will be discussing mental health in tech. We believe in the importance of this project because somebody listening today will be impacted by the work we've done here. But first, let me go over our agenda for today. Our agenda includes an introduction to the amazing team that put this together, a summary and an overview of the data science pipeline. Then we'll go into acquire, prepare, exploration, and modeling. Lastly, we'll go over proposed recommendations, next steps, and resources. First is myself, Lynn Quach. I will be going over the introductions and the summary. Carl Griffin will be going over acquire and prepare. Lupe Luna will be covering exploration and recommendations. Tyler Applegate will be discussing further exploration of the data. And Parker Voigt will be discussing modeling. We performed some background research as to why mental health in the workplace is an important topic. According to LinkedIn, companies with inclusive talent practices generate up to 30% higher revenue per employee. 50% of employees have left a job to get away from a bad boss. The cost of replacing an employee is 1.5 times their salary. And according to data from MetLife, employees with mental health concerns have a decrease in productivity by 26% and engagement by 32%. Our goal was to understand what affects an employee's mental health in the workplace and find solutions that have a positive impact. In addition, we want to normalize how we treat and speak about mental health. Why does it matter? Creating a healthier work environment not only benefits the employees, but the company as a whole. How, you may be wondering? Well, you will make for happier employees who are more productive, increase employee retention, and save money. Our insights include the importance of being able to discuss mental health with your employer without leading to negative consequences, feeling comfortable enough with your supervisor to discuss mental health, the presence, knowledge of, and ability to use support and resources by your employer are important for decreasing work interference. Our proposed recommendations include solutions from the top, such as a more inclusive mission statement, to the bottom, such as policy changes. I will now turn it over to Carl to start the discussion on the process taken to determine our findings.
Thank you, Lynn. We followed best practices in the data science pipeline. First, we acquired the data from the open sourcing mental illness database. In preparation, we took the raw data and prepared it using NumPy and Pandas. To explore the data, we performed hypothesis testing using SciPy with the visualizations of the data through the use of Matplotlib, Seaborn, and Tableau. We used scikit-learn and distributed machine learning community to create our 4 models. As stated previously, our data originated from the open sourcing mental illness database. The data set was from a 2014 survey that measures attitudes and frequency towards mental health in the tech workplace. We started with 1,259 respondents with 28 columns of data. Once we prepared the data, we ended up with a data set consisting of 957 respondents and 28 columns. We only kept North America and Europe due to similar economics and culture. This gave us a more controlled variables with less bias in the data. In addition, we dropped the states and comments columns because we did not have enough data points. We then normalized the text responses. In other words, we attempted to reduce its randomness, bringing it closer to a predefined standard. This helped us to reduce the amount of different information that the models had to deal with and therefore improved efficiency. Next, we knew we needed to encode all categorical variables for our machine learning models. In order to do so, we converted all non-applicable answers to no. Lastly, we converted all categorical variables to numbers, which is also known as one-hot encoding. We did this to the top 13 features to be able to feed these features into our modeling. Next is Lupe to start off our exploration process.
Thank you, Carl. We'll start off our exploration with our target variable, work interference. Work interference here refers to if the employee had a mental health condition and whether or not they felt it interfered with their work. And 63% of respondents reported workplace interference. Next, we'll be looking at the gender distribution. When it comes to gender distribution, 77% of the respondents were male, 22% female, and 1% who identified as neither male or female or did not respond. We will explore deeper by asking a few questions. What are companies doing well? When asked, do you think that discussing a physical health issue with your employer would have negative consequences? 75% of respondents do not feel there will be consequences for bringing up a physical health issue with their employer. When asked, have you heard of or observed negative consequences for coworkers with mental health conditions in your workplace? Almost 90% of respondents reported having never seen or heard of negative consequences for coworkers with mental health issues. Next is Tyler to explain hypothesis and the rest of the exploration process.
Thank you, Lupe. Now that we know what companies are doing well, we will start asking questions and continuing exploration to determine where companies can improve. One of the first things we looked at was company size. Our data set had companies ranging in size from fewer than 5 employees on up to over 1,000. While we found differences between company sizes, none of them were strong enough to suggest an alternate set of recommendations based on the company's size. We did, however, find there are 2 distinct paths. One, the company can directly influence, and another, companies should be aware of, although they cannot directly control for. Some examples of what the company can impact include whether employees feel comfortable speaking with a supervisor about mental health issues, how easy is it to take leave, what kind of benefits are offered, and do they include mental health services. Some examples of variables companies need to be aware of but cannot directly control include whether an employee has sought treatment for a mental health issue in the past, does the employee have a family history of mental illness, how old is the employee, and what gender does the employee identify as. While each of these paths provide value to our models, in this presentation, we are going to focus on a few of the main variables companies can address to positively impact mental health in the workplace. How did we verify our results? We used hypothesis testing, which is a scientific method relying on statistical testing to reject or fail to reject our initial ideas. The first step is to choose the right type of test. The second step is to set our confidence level and form our initial hypotheses. We then use statistical testing to calculate our p-value and test statistics. Finally, we use these results along with data visualizations to draw conclusions. Due to our dataset consisting of nominal and ordinal discrete variables, we are using a chi-squared test to determine dependence of 2 categorical variables. Our confidence level is set at 95% for all tests, and we will only reject our null hypotheses if our p-values are below 0.05, meaning we have a less than 5% probability of our results occurring by chance. Now, we followed these steps for numerous tests throughout our exploration, and I'm going to highlight a few of our key findings now. In order to compare how companies treat mental and physical health issues, the first question we asked is, do employees think discussing a physical health issue with their employer would result in negative consequences? As expected, we see that the answer is no. 3 out of 4 employees do not fear consequences, while 20% are unsure, and less than 5% fear consequences for a physical health issue. Well, how does this differ for mental health? We asked, do employees think discussing a mental health issue with their employer would result in negative consequences? Yes. While 75% of employees didn't fear consequences for a physical health issue, we see that figure has dropped to less than 40% for mental health. Uncertainty has also almost doubled, showing a clear need to effectively communicate company policies. And the fear of consequences has increased almost 5 times. After seeing this stark contrast, we wanted to find out how this difference impacts workplace interference. So we asked, do employees who fear consequences for mental health issues have higher rates of workplace interference? Yes. In fact, those who felt they would face mental health consequences had workplace interference at 77%, which is well above the overall rate of 63%. While those who did not fear consequences had workplace interference at 8 percentage points less than the average of all employees. The next hypothesis we would like to discuss is, do employees who feel comfortable speaking to a supervisor about a mental health issue have less work interference? Yes. We see those who are comfortable speaking to a supervisor are less likely to have workplace interference than those who are not. We also see the need for uniform training among all supervisory staff so employees can feel comfortable regardless of who is or is not in the office. The final hypothesis we would like to go over is, do employees who find it at least somewhat difficult to take leave have higher rates of workplace interference? Yes. What we see is that employees who feel it is difficult to take leave have rates of workplace interference that are significantly higher. In fact, workplace interference drops from 86% all the way down to 58% when moving from the very difficult to the very easy to take leave group, highlighting that it doesn't matter how good your employee's benefits package is if they don't get the time to use it. In our exploration, we followed these procedures, trying to find any and all drivers of workplace interference on both the company and employee paths. Parker will now explain how we decided which of these variables to bring into our initial models.
Thank you, Tyler. Based off of our results from the exploratory data analysis and statistical testing, we went ahead and selected the most significant features as determined by a chi-square test. The top 9 most predictive features of work interference due to mental health were family history, whether or not they received treatment, if they feel comfortable bringing up mental health in an interview, if they are aware of care options for mental health care, if they feel comfortable speaking with a supervisor about mental health, if they believe there would be consequences for discussing mental health, ease of obtaining medical leave for mental health issues, having mental health care included in benefits, and gender. To first begin our modeling, we established the baseline accuracy, using the most abundant class as the predicted value. Our baseline model is 63% accurate in predicting work interference. We then tested 4 different models, with the random forest and multi-layer perceptron performing the best on the validate set. We selected the random forest as the best model due to its generalizability and because it is a white box model. Because our data is sensitive and that we are dealing with mental health, we want to be able to understand how each feature contributes to classification. After using unseen data with our model, we observed an overall accuracy score of 85%. More importantly, it was able to predict 94% of cases of work interference correctly. This translates to a 35% increase in model performance compared to our baseline. To take a deeper look at our model, shown is one decision tree out of 100 in the random forest. As you can see, it is quite complicated and makes multiple decisions to classify one response. In order to get a better look, we chose to take one pathway and to see how it classifies both cases of work interference. Ease of obtaining leave is a common separator seen at multiple levels of depth in the model, implying that it is a stronger predictor than some others. Being open with the supervisor and not believing that there would be consequences for discussing mental health are other important predictors in this branch of the tree. The model leaves end in classifying a response as either experiencing or not experiencing work interference due to mental health. Now, to determine feature importance, we used 2 separate methods. The first was using mean decrease of impurity. Impurity is the probability of a feature misclassifying an observation. An MDI analysis works by removing a feature from the model and then measuring the change in probability of misclassifying an observation. The greater the change, the more important the feature is for predicting work interference due to mental health. The second method was a permutation importance analysis. A permutation importance analysis works by randomly shuffling one feature and then measuring the change in the error rate of the output. Similar to an MDI analysis, the more important a feature is, we will see a greater change in error in predicting work interference. We decided to perform 2 feature importance analyses for validation purposes. The MDI analysis shows that family history, ease of obtaining medical leave for mental health, options for mental health care, perceived consequences for discussing mental health, and openness to discuss mental health with a supervisor are the top 5 most important features. Keep in mind, these are the average decrease for all 100 trees in the forest. The results from the permutation importance analysis show the same top 5 features. The box plots represent the range of error rates produced from shuffling each feature. Both feature analyses show that the family history of mental illness is the most predictive, followed by the ease of obtaining leave, care options, whether or not discussing mental health results in negative consequences, and the ability to speak with the supervisor about mental health, and they all contribute to mental wellness in the workplace. And now over to Lupe with some recommendations.
Thank you, Parker. We will now conclude our presentation with our recommendations and next steps. As mentioned earlier, although there are 2 distinct paths of drivers of workplace interference, one that the company can directly control and the other that is somewhat out of their hands, we are proposing a comprehensive list of recommendations that addresses each of these paths in conjunction. Review mission statement. Have a mission statement that shows inclusivity for mental and physical health assistance. Management should visit their mission statement to make sure it includes the care of mental health for all. Adopt a holistic approach to health. As previously stated, our data shows that 75% are not worried about physical health consequences. This should be the same for mental health. Management and training resources. Training management to help them recognize the signs and symptoms of stress and depression in team members and encourage them to seek help from qualified mental health professionals. Onboarding procedures. Mental health can be mentioned during the onboarding process for new employees to make them aware that services are available and that the company does care. Ease to use leave and benefits. Since only 35% of employees found it somewhat easy to take leave, employers should reevaluate this benefit and their restrictions. Resources and employee services. Employers can distribute materials such as brochures, flyers, and videos to all employees about the signs and symptoms of poor mental health and the opportunities for treatment. Our next steps would be gather more data on employees' financial status and their role in the company. It would also be interesting to collect the most current data to see a more accurate representation to our current conditions with COVID and how the gender gap has evolved since this 2014 survey. Here we have a list of resources we use that helped us verify our recommendations and resources for employers to help guide them in the process of improving mental health in the workplace. Thank you from the Tech Blues team. If you would like to know more information about the individuals that presented here today, please refer to the Codeup alumni portal. And keep in mind, healing doesn't mean the damage never existed. It means the damage no longer controls your life. Thank you and have a wonderful day.
At Codeup, we don't just teach statistics, SQL, Python, and various other tools. We also teach our students how to learn and approach new problems with perseverance and self-reliance. This is what builds adaptable professionals. They can learn to use whatever tools they have to create meaningful solutions for their companies. This adaptive expertise is often referred to as learning agility, one of the most highly sought after qualities in the tech field. As you watch our next presentation, you'll see how this group turned a problem into an innovative solution. Here's team Attention Walmart Shoppers.
Attention Walmart shoppers. For a moment, put yourself in the shoes of a store manager. You'd really like to know what your sales numbers will be for the next week, and you know that unemployment has been up in recent weeks, but you don't know how that will affect your bottom line. Well, our team set out to solve that very problem. Hi, I'm Heather McMillan, and today my team and I are going to walk you through our successful weekly sales prediction model. First things first, let me introduce you to our team. We have myself, Heather McMillan, Natasha Rivers, Cindy Villanueva, and Alberto Puentes. All the members of this team worked tirelessly to bring you this report today. And while we have split up talking about this project, we all worked on every phase of the data science pipeline, from acquiring the data to gaining insights from exploration and creating machine learning models. I'm going to start us off today with an executive summary and a brief intro into our data. Then Natasha will expound on our explorations and findings. Cindy will get to the meat and potatoes, our machine learning model, and Alberto will finish us out with how our work can have an impact. Why should you care about our Walmart data analysis? You don't work for Walmart. Well, this is a common business problem, and we tackled it. Our goal was to create a model that predicts sales 1 week out, taking into account historical sales, inflation indicators, and seasonal trends such as holiday sales. It's flexible to be tailored to suit other businesses and powerful in its predictions. How did we do it? We engineered features to capture the historical data and seasonality. We found that historical sales data, such as sales from the previous year, in conjunction with month-over-month consumer price index averages and various holiday indicators, were a big determining factor for accurately predicting future sales. So, what did we find? Well, in addition to noticing trends in the data, we were able to create a regression model that beat an already impressively accurate prediction method, predicting with last year's sales by 29%. We started out on this journey by acquiring Walmart data from a Kaggle competition. The data included total sales numbers by week for 45 different Walmart stores. Then, we tackled the biggest challenge of our entire project, transforming time series data into data that was regression ready. To do this, we engineered features that captured the time data in one observation. By taking weekly sales information from 1 week and shifting it back in time a week, we created a way to capture the economic information up to the point of prediction, as well as giving our model something to aim for. We used this method to create a number of features to include sales from a week ago, sales from a year ago, rolling monthly and quarterly averages of unemployment numbers, gas prices, and inflation indicators. We ended up with 34 columns and 6,435 rows of data, spanning from February of 2010 to October of 2012. Because we created a column that was called last year's sales, we couldn't use the first year's worth of data for modeling. That left us with 64% of our data to train and test our model. The data was then shuffled around so that we could predict any instance of next week's sales. How did we come up with these features, and which ones did we use for our model? Well, Natasha is going to lead us through how we explored this data and what we found.
Thank you, Heather. To reiterate, we set out to build a predictive model to determine sales 1 week out. This model can help managers maintain proper inventory levels, thus increasing profits for the stores and improving the customer experience. To prepare the data, as Heather discussed, we used Python and Pandas and continued to use those tools into the exploration phase, where we brought in Seaborn, Tableau, and Matplotlib to leverage their powerful visualization capabilities. We created several new features to capture the data, but we had to determine which features would have significance when working in conjunction with scikit-learn's dynamic algorithms to create our model. While exploring the data, to our surprise, the week of Christmas showed a significant dip, while the weeks priors had a significant spike, as the visualization shows us. We continued to look into this and realized its importance. With this, a new feature was created called Pre-Christmas. Another obstacle that we had to overcome while exploring this data was dealing with multicollinearity among our engineered features, meaning the independent variables, also known as predictors, are highly correlated with one another, so the effects can be obscured. Essentially, two features have so much in common that their predictive abilities overlap, thus potentially skewing our results. Because of this, we ended up dropping several of those engineered features. After all statistical testing was complete, we found evidence to support that last week's sales, last year's sales, and the pre-Christmas spike do have an impact on next week's sales. What do we have to back this up? Well, our methods included completing Pearson's correlation testing and t-testing with a confidence of 95% that our results did not occur by chance. Now that we've dealt with all of these factors, we have our clean data frame, but what do we do with it? How can we predict sales for a Walmart store next week? Well, we use recursive feature elimination and select k-best in order to find the best features to use in our modeling phase, leading us to keep some features and drop others. Those features included historical sales data, meaning we would use previous sales to predict future sales, holiday indicators such as Super Bowl, Labor Day, Thanksgiving, pre-Christmas, which was the feature that we created, and Christmas. And lastly, unemployment rates, primarily 4-week rolling averages, quarterly percentages, and monthly percentages. We called these our drivers. We went back through the exploration phase several times in an attempt to better capture our data. In the end, we believe we created a pretty decent model. Cindy, take it away.
Thank you, Natasha. We did create a pretty great model. Our model beat our baseline by 29% of root mean square error. How did we get there? Well, first, we established a baseline using last year's sales numbers only. Then, we built 4 models, and in order to compare them, we used the metric root mean square error, and we wanted the lowest value possible. The best model was polynomial regression second degree. Why did we use linear regression models? Because the next week's sales are a continuous value, and the essence of the linear regression is to find the line that best fits the data points, so that we can know the value is likely to fall in the future. The best line is the one that has very low residuals, which is the difference between observed and predicted values. But what happens if we have this type of data? Well, this is similar to our data. In this case, we use polynomial regression because it gives the line a curvilinear shape so it can better fit our data by increasing the power of a single feature. But be careful, the more degrees you add, the more overfit your model becomes. Let's see how the polynomial features were created. It creates new features from the original features, so we can get combination of 2 features, square features, and single features. These are the top features our model took into consideration. We can see combination of multiple features, a feature by itself, and a features square. Notice we can see what we found in exploration. Holidays have a big impact on our predictive modeling. After we trained our model, we tested it on unseen data. Here we have results from store number 7. The blue targets represent the actual sales numbers that we are aiming for. The yellow B is our baseline, which is not bad at all. Now, here are the predictions. We can see that they were closer than the baseline. The closer, the better. We created this wonderful model, but what can we do with it?
I can help with that, Cindy.
Thank you, Alberto. Take it away.
In order to answer that, I first have to recap how we got here. For every sales point, we accounted for 3 factors: base demand, trend, and seasonality. As a base demand proxy, we referenced the sales data 1 year prior. In doing so, we could already explain roughly 97.5% of the variance in our sales data. Mission accomplished, right? Not exactly. Just because we've established that the baseline is a strong predictor, it doesn't mean that we built a model that can be utilized in a real-world situation. So how do you improve on that baseline? By leveraging the insights gained during exploration, we utilized the features we had to engineer new features, iterated through multiple scenarios, refining and evaluating along the way. Earlier, you heard Tasha speak about some of the feature engineering steps we took during preparation. In our analysis, we didn't visually identify any significant long-term trends, but accounted for this potential influence through the construction of rolling indicators measuring month-on-month and quarter-on-quarter changes. These enabled our model to pick up on shifts in the data trends and will enable the model to adjust accordingly going forward. As Cindy pointed out earlier, the month-on-month change in the CPI was identified among our top 10 features. When initially reviewing the data, we were immediately forced to think about how we were going to account for the strong seasonality in our sales data. Sounds easy enough, right? But organizing the data in a way that would enable the model to account for the different holiday impacts was our biggest challenge and success. The Christmas and Thanksgiving sales spikes alone were so strong they looked like they could be anomalous. We had to train our model to adjust utilizing the new features like our pre-Christmas indicator that would flag the unique 2-week run-up in sales leading into the Christmas holiday. Now let's get back to the store manager Heather mentioned earlier. How do they deal with sales data that suggests demand can change more than 25% week over week or from 1 month to the next? On its face, this sounds unmanageable, but fortunately for them, we've broken down the sales data, analyzed the drivers, and modeled the demand. The result of our work is a model that can accurately forecast sales demand 1 week in advance and accounts for 98.5% of the variance in the historical sales data. Nevertheless, a 1-week predictive window has its limitations. On its own, our model can't address the forecasting needs beyond a 1-week horizon. Therefore, our recommendation is that our model be deployed in a blended strategy. We recommend utilizing last year's sales data as a base predictor for decisions that need to be made beyond a week's horizon, and employing our model to refine and adjust those inventory decisions 1 week in advance.
We believe the accuracy in our model, combined with the flexibility of our model benchmark, will result in the most efficient supply distribution for not only that individual store manager, but for the logistics manager supervising multiple locations.
That's right, Alberto. We will be able to help out those managers and shareholders with a more precise model. We found that various holiday indicators and historical sales data were proven to be powerful information for predicting the future. I'd like to thank you all for taking the time to listen to our presentation today. If you'd like to look at our code, you can check out our GitHub repo. And if you'd like to explore the visuals seen here, check out our Tableau dashboard. Thank you all for shopping. And
Have a nice day.
There you have it. That concludes today's Capstone presentations. Thank you to everyone for joining us to see the impressive work our graduates are capable of. If you're an employer that's ready to hire a data scientist trained in the most in-demand skills, head over to alumni.codeup.com to find resumes and contact information of the graduates. Or you can email us at partners@codeup.com and we'll get you on the right track. Family and friends, stay tuned to see a little bit more of the graduates as they reminisce on their favorite Codeup memories and thank their supporters. A private Zoom room celebration will follow these videos.